Good morning, folks. Welcome to physics. We are starting our new unit on acceleration today. But in order to move forward, it's helpful to look at where we've come and what models we have used so far in order to talk about physics. Let's start with a quick review. Take a minute to consider the two graphs below. Number 1 is a position graph, and number 2 is a velocity graph. On some scratch paper, sketch what a motion map for each of these two motions would look like. Remember, a motion map is the diagrams that have all the little arrows showing the direction and the amount of something's velocity. Pause the video, draw your diagrams, and then press start. All right, let's check your work. In question number 1, you should have drawn something that looks like this. The motion starts off slow and moving forward, and the second portion of the motion is moving faster, so we have larger arrows still pointing in the same direction. In the second graph, we have a velocity that is negative. That means that this object is moving backwards. The first portion of the motion is moving faster, so the arrows are longer, moving to the left. The second portion of the motion is slower, so we have smaller arrows still pointing to the left. Towards the beginning of the year, I introduced you to the idea of scientific models. These are basically mathematical arrangements that describe a particular situation. In some ways, we can describe physics as the process of modeling motion using mathematics. We've considered several models in our class so far. We started with a model of constant speed, then talked about the model that includes conserving momentum, and finally, we just finished looking at models where we have balanced forces that lead to constant velocity motion. Let's take just a second and review what we've talked about with each of those models so far. The first model we talked about was constant velocity motion. We started off looking at graphs of position versus time and found that with constant velocity motion, we always had linear graphs. And the slope of those graphs, the rate at which the position was changing, we called velocity. We also talked about the fact that the y-intercept of these graphs would tell us the beginning or initial position of an object. We modeled motion using an equation like this. Position is equal to velocity multiplied by time plus the initial position. We sometimes sketched velocity graphs as well, but since our objects had constant velocity, we ended up with pretty boring, mostly horizontal graphs. We defined velocity as the rate at which position is changing, or the change in position divided by time. After our unit on constant velocity, we moved on to talk about momentum. We defined momentum, the variable p, as mass multiplied by velocity. This was particularly helpful when we looked at collisions, and we found that in a collision, the initial momentum of the entire system would be equal to the final momentum of the entire system. We called that the conservation of momentum and wrote it this way: the sum of the initial momentum equals the sum of the final momentum. We also looked at objects individually in this unit and found that for any object, its change in momentum or its impulse was equal to the force applied to it multiplied by the time the force was acting. The unit we just completed was about balanced forces. Here we considered lots of different types of forces that could be applied to various objects and modeled them using free body diagrams like the one that is shown here. We found that when the net force on an object was equal to 0, the object's velocity would remain constant. This is Newton's first law. Let's look at this example. Here we have a truck smashing into a car and moving off at a constant velocity after the collision. How would each of the models we have discussed relate to this example? Take a moment, pause the video, and sketch as many graphs and diagrams as you can that could model this situation, either in parts or in whole. There are several ways you may have modeled this situation. Perhaps you drew some position time graphs. You probably noticed that at the beginning, the truck was moving forward with a constant velocity, and the car was sitting still, so its velocity was equal to 0. After the collision, both vehicles moved, but with a velocity that was slower than the initial velocity of the truck. Perhaps you drew force diagrams. You would have drawn before the collision that the truck had a net force of 0 since it was moving at a constant velocity. You would have drawn possibly a force diagram that looked like this, with the force of gravity and the normal force. Perhaps you put in the force of the engine and the force of friction balancing each other out. After the collision, you would have drawn something similar. Normal force and force of gravity, and perhaps the force of the engine and the force of friction, again balancing each other out. During the collision, you would have drawn a force diagram for the car that showed the force of gravity and the normal force, but then an overall force, a net force from the truck on the car. Perhaps you looked at this from the perspective of momentum. You would have said that the momentum of the truck before the collision was equal to the momentum of the truck and the car after the collision. This is simply adding up the momentum before the collision and saying that it is equal to the momentum after the collision. Let's consider another situation that we might model using what we have learned so far in physics. Consider this horse skidding to a stop. How would the models we have discussed so far be able to describe this situation? Take a moment, pause the video, and see what descriptions of motion you can draw. Here are some of the things you may have drawn as you were attempting to model this situation. Perhaps you drew a motion map. In this case, since the horse is slowing down, we would have needed to draw arrows that are getting shorter and shorter as time goes past. Perhaps you drew a motion graph. This graph of position versus time shows an object that's slowing down. Notice that the slope is not constant. The slope is constantly getting smaller as the velocity gets smaller. Perhaps you drew a graph of velocity versus time. In this case, the horse's velocity is changing. So we started off with a positive value for velocity since it's moving forward, and gradually that velocity got closer and closer to 0 as the horse skidded to a stop. Perhaps you drew a force diagram or a free body diagram. You would have drawn something like this: the normal force and the force of gravity acting on the horse, as well as the force of friction, slowing the horse down. This is a case where the net force on the horse would have needed to be not equal to 0. Models we have looked at so far don't describe this situation quite in as much depth as we could. In order to describe something where the velocity is changing, we need a new term. What do we call it when something's velocity is changing? The common term we use is acceleration. So in this unit, we will add the notion of acceleration. What do we mean by acceleration? Well, colloquially, we mean when something is speeding up or when something is slowing down. When something is speeding up, we typically have a velocity that's getting farther and farther from 0. When something is slowing down, we find a velocity that's approaching 0. When we talk about acceleration, what we really mean is the rate at which the velocity is changing. How quickly is the velocity changing as something is speeding up or slowing down? Mathematically, this means that we are looking for the change in velocity divided by the time over which that change takes place. That means that the units for our acceleration are the units of velocity, meters per second, divided by a unit of time, often seconds. That gives us a sort of strange unit, meters per second per second. Sometimes we will combine the units of seconds and write this as meters per second squared. Let's consider an example. Let's say you're driving down the road and see a deer. You slow down from 25 meters per second, that's about 60 miles per hour, to 5 meters per second, that's about 11 miles per hour, in 2 seconds to avoid a collision. What is your acceleration? Take a moment, pause the video, and work out your solution. As you picture what's happening to the velocity in this situation, we know the velocity is decreasing from 25 to 5. The graph would look something like this, and our change in velocity here would be negative 20 meters per second. That means the acceleration would be the change in velocity divided by time, in this case, negative 20 meters per second divided by 2 seconds, to give us negative 10 meters per second per second. We could also have written that as negative 10 meters per second squared. Let's look at another example. During its takeoff, the Apollo 11 rocket had an acceleration of 127 feet per second squared. Assuming it started from rest, find its velocity after 1, 2, 3, and 4 seconds. Pause the video and work out your solution. An acceleration of 127 feet per second squared means that every second its velocity increased by 127 feet per second. So starting from rest, after 1 second, the velocity would be 127. After 2 seconds, the velocity would be 127 more, meaning 254 feet per second. Adding 127 again gives us a velocity of 381 feet per second. And finally, after 4 seconds, the rocket would have had a velocity of 508 feet per second. But to make it into orbit, the maximum speed Apollo 11 reached during stage 1 was 7,883 feet per second. With this acceleration, how long would that have taken? Pause your video and work out your answer. In order to determine how long this would take, we'll consider the equation for acceleration. Acceleration is the change in velocity over time. We can solve this for the change in velocity and write that the change in velocity is the acceleration multiplied by time. That means that to go from 0 to 7,883 feet per second with an acceleration of 127 meters per second squared, it would take 62.1 seconds, or just over 1 minute. We will continue talking about acceleration over the next several lessons. We'll develop more sophisticated models of graphs and motion maps in order to help you solve questions like this. In the meantime, take the quiz associated with this video and have a great day.